So you made it through chapter 2, and you now are familiar with the 5 kinematic equations that you're going to know and love before you're done with physics, or you'll never be done with physics. So you're going to just love those equations. And what they basically dealt with was kinematic motion, translational motion in a one-dimensional direction, either positive direction or negative direction. So direction mattered as far as positive or negative along a one-dimensional direction. Well, we wish to expand that to 2 dimensions or possibly 3 dimensions. To do that, we need better mathematics. And hence, we are going to introduce a mathematical convention called vectors. Before we get there, let's recall what a polar coordinate system will do for us. Take a look at this graph here. We have a Cartesian coordinate system, and we have labeled a point, x and y, based on its coordinates for Cartesian coordinate system, x and y. I can draw a line from a origin to that point, and the length of that line I'm going to call r, and the angle of that line from some reference point, say the positive x-axis, I'm going to call that theta. So I can actually redefine this point in terms of 2 other variables, the length of this line and the angle from some reference point to that point. So that just as equivalently labels that point. So I need 2 variables either in the polar coordinate system, the length and the angle, or 2 variables in the Cartesian coordinate system, x and y. Now if I look at this right triangle here, I can see that x is one side of that right triangle, and it's actually equal to the hypotenuse r times the cosine of theta. And for that matter, y is equal to r times the sine of theta. So I can get x and y from the values of r and theta. And working in the opposite direction, I could say that y divided by x is equal to sine of theta divided by the cosine theta, otherwise known as the tangent theta. Take the inverse tangent of both sides, and I have that my angle theta is equal to the inverse tangent of my rise over my run, y divided by x. So if I knew x and y, I could get the angle theta by this, the inverse tangent of y over x. Also, I could square x, so I have x squared equals r squared cosine squared theta, and square y, so that y squared equals r squared sine squared theta. So x squared plus y squared equals r squared cosine squared theta plus sine squared theta, which is just a fancy way of saying 1. So x squared plus y squared equals r squared, or r is equal to the square root of x squared plus y squared. And hence, if I knew x and y, I can get this length r by taking the square root of x squared plus y squared. So I can convert from a Cartesian coordinate system, x and y, easily to a polar coordinate system, r and theta. This is important not only for this new coordinate system, but this is the kind of mathematical techniques we want to use if we're going to be using vectors. Let's try this out. The Cartesian coordinate systems of a point are x equal to negative 3.5, y equal to negative 2.5. We wish to find the polar coordinates to this point. Well, let's find r. That's going to be the square root of x squared plus y squared. So square root of negative 3.5 squared plus negative 2.5 squared, square root. The negatives, when they're squared, are going to be positive values anyway. And this will give us a r of 4.3 meters. And then for my angle theta, the inverse tangent of y over x will give me 216 degrees from the positive x-axis. Actually, if I actually did this on my calculator, and I put in a negative 2.5 divided by a negative 3.5 inverse tangent, my calculator would give me 36 degrees, because it doesn't have a brain, so it doesn't know what's going on. It doesn't know that you actually divided a negative number by a negative number and were actually located in the third quadrant. So it's going to think that they both were positive, and it's going to give you an answer in the first quadrant of 36 degrees, where the true answer should have been 180 degrees more than that, because they're both negative. So you have to be careful. If I were doing this kind of problem, I would simply find the angle in that third quadrant of 36 degrees and then just realize that I'd be 30 degrees, south of west, if you consider it that way, or 36 degrees below the negative x-axis. That's the way I would do the problem. All right, so with that little introduction with the polar coordinate system, we wish to get into vectors and scalars. Now, a scalar is something that has only magnitude and no particular direction associated with it. An example of a scalar is temperature. If I talk about the temperature of this room, it's actually a little bit chilly in this room right now. I could say it's 68 degrees, and everywhere where I'm located in this room, I would associate that temperature, 68 degrees. So it's just a number associated with some quantity. Volume. If I talk about the volume of this room, so many cubic feet or so many cubic meters, it would just be a number associated with the actual volume of this room. The direction doesn't matter whether I go east, west, north, south in this room. It doesn't matter in the total quantity of the volume. Mass. The mass is something, just a quantity. It's just a scalar value. It doesn't matter the direction, right, left, up, or down. Energy is just a quantity of energy, right, left, up, down, forward, back. Doesn't matter. Work is a form of energy, so the same thing. All these things are scalar quantities. They only have magnitude. Time interval, amount of time that you have, just a magnitude of something. So these are all scalars. On the other hand, a vector is a quantity that has a magnitude and a direction associated with it. Vectors are indicated in general by placing an arrow over the quantity or by using boldface type. So we would call this vector A, and we have to put an indication that it's a vector over the quantity, so it's vector A. Graphically, vectors are represented by an arrow. The length of the arrow gives us the magnitude, and the direction of the arrow from some reference point, in this case the positive x-axis, gives us the direction. So it's like a polar coordinate. You have a magnitude and an angle, and that is representing our vector. Examples of vectors are displacement. It matters if I change my position and say I go 100 miles north to Nashville, or if I go 100 miles south to Birmingham. I'm going to end up in different places, and my displacement is going to be different. So the direction matters whether I go north or south. Velocity. It's going to matter if I go 50 miles per hour north and end up in 2 hours in Nashville, or 50 miles per hour south and end up after 2 hours in Birmingham. So velocity matters, and it actually is, velocity is displacement per time. So because I divide a vector by a scalar quantity time, I still end up with a vector. Acceleration is my change in velocity over time. And so again, I'm taking a vector, velocity, and dividing it by time and coming up with a vector. So any kind of modification like that will give me another vector. Force is mass times acceleration. We haven't gotten into that yet. That's going to be chapter 5. But I'm just multiplying the acceleration by a scalar quantity, mass, and I'm getting force. And that is in itself a vector. So all these things are vector quantities. If, for instance, for force, if I were flying an airplane and there was a wind pushing me from the back, that would give me an acceleration and would actually pushed me to a certain location, as opposed to, say, a crosswind that was pushing on me and making me go off to the right somewhere. So I'm going to end up differently with those two different forces. They could be the same magnitude force, but they have different directions. So direction matters. Here are some properties of vectors. To say that A is equal to B means that both the magnitude of A and B are the same and that they are in parallel directions. Here's vector A. I'm designated by A with an arrow over it. I have magnitude and direction. Excuse me. Here's vector B, also magnitude and direction. If I compare the magnitudes, they're the same length. So they have the same length. And if I look at their directions with respect to some reference, in this case the positive x direction, they have the same angle. So even though they're not on top of one another, they are parallel, and they have the same magnitude, and they are indeed the same vectors. So I would say that A is equal to B in this case. Two or more vectors are added tip to tail, and the resultant vector extends from the tail of the first vector to the tip of the last vector. Here's an example. Here's vector A. I'm going to add vector B to it, and add vector C to that, tip to tail. So I end up A added tip to tail to B, added tip to tail to C, and I go from the tail of A to the tip of C, and that's my resultant vector. So as vectors go, A plus B plus C is equal to R. Or I could write it like this. Vector A plus vector B plus vector C is equal to R. All the while, these vectors are representing magnitude and direction by the arrow themselves. And adding them tip to tail represents magnitude and direction. I end up with the resultant vector as my result. The negative of a vector, negative A, and incidentally I should be having arrows over these vectors, but in my font of this, in my font I wasn't able to put arrows on this particular writing, but I do have it down in the diagrams down here. The negative of a vector A is a vector that has the same magnitude, but 180 degrees opposite direction. So here's A and here is negative A. Exactly the same length, the same magnitude, but 180 degrees opposite direction, just the opposite direction. So if I look at this, and if I were to add A plus a negative A, in other words, A added tip to tail to a negative A, I'm going to end up right back where I started. So in other words, A plus a negative A, which would be the same as A minus A as a vector, is equal to 0. And that makes sense. If I take a vector A and multiply it by a positive scalar, quantity m in this case, the product, scalar times vector, is a vector that has the same magnitude as A, or same direction as A, and a magnitude equal to the scalar times A. For instance, let's say I have 2 times vector A. That's going to be equal to A plus A, 2 A's, all in the same direction. So in essence, I end up with a vector that is twice as long. That is equal to 2 times A. So what the scalar does is change my magnitude, but it doesn't change my direction. So we know a vector can be a sum of other vectors, and in particular we want to treat a vector and treat it as a sum of component vectors. For instance, let's take a look at this on a two-dimensional level. Here's my x and y Cartesian coordinate system. I have a vector A like this. I'm going to express A as the vector sum of 2 smaller vectors, A sub x and A sub y. A sub x added tip to tail to A sub y comprises vector A. So I can write it in vector form like this. A is equal to A sub x plus A sub y as vectors added together. I'm going to want to do this a lot. So, to try to indicate direction, either x, y, or z, I am going to use unit vectors to indicate these directions. We will define a I unit vector in the x direction as a vector only having that direction in the x direction and having magnitude 1. So the I unit vector is a vector, magnitude 1. Since it's only magnitude 1, we indicate our unit vectors not with an arrow, but with a hat. So a little hat just means it is indeed a unit vector of magnitude 1. I is in the x direction, j is in the y direction, and k is in the z direction. All these are trying to do is indicate directions, either x, y, or z, I, j, and k. We will give them magnitude by multiplying them by a scalar number. So, under that idea, we can represent an arbitrary vector A in unit vector form as being A is equal to some scalar A sub x times I plus another scalar A sub y times j plus another scalar A sub z times k. All the A sub x, A sub y, and A sub z do is give each component a magnitude, because the original unit vector has just magnitude 1. So by adding these three component vectors in the I, j, and k direction, we can comprise a three-dimensional vector. So A is out there in three-dimensional space. We have our three component vectors, A sub x I, A sub y j, A sub z k. Adding those three vectors tip to tail will give me this vector A in three-dimensional space. Let's try this in 2 dimensions just to see it more clearly. I'm going to say my resultant vector is equal to A plus B, and we want to add these together. So we represent A as two component vectors, A sub xi plus A sub yj. I'm going to do the same thing for B. B sub xi plus B sub yj. Add these together. If I do that, at least in the I direction, my components are either positive or negative compared to each other. It's like a number line. So I can add them together, either positive or negative, and I'm fine adding them together just almost like they were scalars, because I'm either positive or negative along the x direction. Same thing for the y direction. My y components will add either positive or negative along the y direction, and that's perfectly fine. And by using it this way, I can simplify these components. So I have A sub x plus B sub x is my R sub x, and A sub y, B sub y is my R sub y. Those are my resultant components of my resultant vectors. So I write this. Resultant vector is R sub x, I, plus R sub y, j. And I have a magnitude times a direction for each component. Graphically, this might look something like this. Here's my vector A with the respective components, A sub x and A sub y, and do the same thing for B. Here's my vector B with components B sub x and B sub y. If I were to add these two vectors together, say B plus A, in a graphical sense, I would end up way over here from the origin. But in terms of mathematics, I would add my components together and get my resultant components. So A sub x plus a B sub x will give me an R sub x, and A sub y plus a B sub y will give me an R sub y. Those are my resultant components, x and y respectively, and they comprise the components of my resultant vector, R's R. So I can look at this graphically as magnitude and direction in the vector B plus A giving me R, or component-wise, R sub x plus R sub y gives me R. Either way I look at it, it's the same. So this gives us a method for adding vectors. We wish to select a coordinate system, sketch and label each vector, find the x and y components of all the vectors involved, add up all the x components of all the vectors, and get the resultant component. What's nice about this is we're only dealing one-dimensionally in the x direction, so they're adding like scalars, positive or negative. Add up all the y components and find the resultant y component, and they're just adding like scalars, positive or negative, to get the resultant y component. And then now I have a resultant x and resultant y. Use the Pythagorean theorem to find the magnitude of this resultant vector, because those are by design perpendicular. So x squared plus y squared will equal the magnitude squared. Take the square root of that, and that'll give me the magnitude of the resultant vector. And use a suitable trig function to find the angle of the resultant vector that it makes with some reference. Normally the positive x-axis, but it could be from the negative x-axis or from the vertical. Anything you want to use as your reference, just so that you're correct. But we want to find a trig function to find that angle to determine our direction. You should be able to handle vectors in the following forms. A vector could be a ordered pair, 3 and 4, which just means that A is equal to 3i plus 4j. You might see a vector in that form in some future engineering course. Or in this course, we are definitely going to be using the ijk form. So we'll say vector A is equal to 3i plus 4j. And remember, again, in my font of this, I wasn't able to put an arrow over the A or a hats over the I and J's, but you should. So that's the way we should write these vectors. And you might see a vector in the form of a magnitude and angle, like polar coordinates, and that would represent the same vector as well. All of these are equivalent, and in future courses you might see vectors of these forms. Now we're going to use ijk, but when you get into a future course and you're using a different form, it might be foreign to you for a couple of days, but once you get into it, it'll just become natural to see vectors in a different form. So you just become comfortable in one form, and then you can adjust to the other form pretty easily. The magnitude of this last vector is equal to 3 squared plus 4 squared square root, or 5. And its angle would be the inverse tangent of the y over the x, in this case 36.9 degrees. So I would write this last vector as 5 angle 36.9, and that would represent the same vector. But like we said, we're not going to focus on that method for this course, but it's just something to keep in mind as you proceed onward. All right, so let's try an example problem. A dog searching for a bone walks 3.5 meters south, then 8.2 meters at an angle 30 degrees north of east, and finally 15 meters west. Find the dog's resultant displacement vector. So we can think of this. Here's our dog moving 3.5 meters south. That would be one vector. And then 8.2 meters at a 30 degree angle north of east. So I look at east first, and then I go 30 degrees north of it to determine the direction of this vector. That's the way you have to work. And that will have different components, x and y, associated with it. And then my last vector is 15 meters west. So that would be totally in the negative x direction. And that will be my third vector. So we want to find the addition of these three, which would be the resultant vector from the origin to the tip of the last vector. I could find all my x components. For the first vector, it's 0 plus 8.2 times the cosine of 30 degrees, and then a minus 15 as I go totally in the negative x direction, giving me a total component in the x direction of a negative 7.9 meters. Do the same thing for the y direction. I'm going a negative 3.5 for my first vector, then I'm going up 8.2 times the sine of 30 degrees, and then my last vector has no y component. I could think of it as 15 times the sine of 90 degrees, or sine of 0 degrees if I wish, and that would be 0. So I have a 0.6 meter y component. So my ultimate resultant components are negative 7.9 and 0.6 meters up. The magnitude of that vector is going to be the square root of 7.9 squared plus 0.6 meters squared, square root, 7.92 meters. And my angle will be inverse tangent of my y over my x. I have 0.6 over 7.9. I left the negatives out because I just want to find the angle first. Inverse tangent is 4.34 degrees. Now I have that angle, and I know it's upward from the west direction, so it's going to be 4.34 degrees north of west. And that will be my angle. I could redefine that if I wished as 85.66 degrees west of north. That'd be another way that I could define that angle, but they're the same angle. So either way I define it is correct. So in this case, I really didn't show you the vectors involved. I have a negative 3.5j, and then I have a vector going up with two components. I guess it was, it's hard to say, 8.2 cosine 30i plus 8.2 sine 30j was my second vector, and then my last vector was a negative 15i. So these are three vectors I add together to get my resultant vector and my resultant displacement based on that. Take a look at the problems in the problem set for Chapter 3, and there'll be plenty of examples to get ideas of how to work with vectors. This is important because we wish to expand kinematics from one dimension to two and possibly three dimensions. So take a look at that.